Hi everyone, my name is Ahmed Nabi. I am a second year PhD student at CBAS, Virginia Tech. My research interest is on the design and control of high frequency LLC resonant converters. 48 volt bus converters are widely used in many applications, such as aerospace and military application, and also used in the IT field, such as in wireless networks, server and data centers, and telecom. The power consumption of the IT sector alone is increasing by the year, and now it represents more than 4% of the global electricity consumption. Saving a fraction of this power is significant, and that's why high-efficiency bus converter is important. Here, we propose single-stage LLC resonant converter for a 1 kilowatt 48 volt to 12 volt bus converter. With LLC resonant converter, we can achieve soft switching and Gauge switching frequency higher than 1 MHz. The LLC is designed with matrix transformer implemented with PCB winding and integrated with high resonant inductance value for regulation. The converter can achieve efficiency of 97.8% and power density of 700 watt per cubic inch. The input voltage for this bus converter ranges from 40 volt to 60 volt, and the output is repeated at 12 volt. This makes the LLC operates at wide gain range from 0.8 to 1.2 and a wide frequency range from 0.8 MHz to 1.8 MHz. The control of high frequency LLC over such a wide frequency range is challenging. Here we propose control method using simplified optimal trajectory control with a new feed-forward compensator to achieve fast transient response over wide input voltage range and wide switching frequency range. On the left, the trajectory of LLC of the resonant inductor current and resonant capacitor voltage is showing. For example, during transient from light load to heavy load, the SOTC controller charges the resonant tank to the vicinity of the heavy load energy. Then, a feed-forward is used to realize the switching frequency of the new state point and resets the frequency of the BI controller. Then, a low bandwidth BI controller is used for fine regulation around the new steady-state load. This control method can achieve fast transient response as compared to linear control method, and optimal transient response is achieved over wide input voltage range. Is a prototype for 1 MHz 1 kilowatt bus converter implemented on a standard quarter brick size. The power density is above 700 watt per cubic inch. Here is the input side, and this is the primary side devices using parallel gain transistors. This is a magnetic component which integrates a matrix transformer with resonant inductor, and here are 4 output sets which are connected to a 12 volt load. On the other side of the converter, we have the digital control circuit with simplified optimal trajectory control. A low-cost, low-speed microcontroller can be used to implement this control method, which is good for high power density solutions. Here we have the transient response results. First, we show the transient response of a commercial 130 kHz bus converter using phase shift topology. This is a 50% to 100% load transient. And here is the transient response for the proposed 1 MHz bus converter using LLC with simplified optimal trajectory control at 48 volt input voltage. The transient response is much faster than the state-of-art solutions. Here is the transient response using the simplified optimal trajectory control at 60 volt input. The transient response is slow. However, here with the proposed control method using feed-forward in conjunction with the simplified optimal trajectory control, a much faster transient response can be achieved. In this short video, we proposed a high-efficiency, high-power density bus converter using LLC resonant converter with fast transient response using digital control. Thank you for watching.